The pH scale from 1 to 14 is probably a scale that you're relatively familiar with, but you may not know where those numbers are coming from. The term pOH is probably a new term to you, but we'll define it and look at how it relates to pH in this lesson. The pH of a solution is the measurement of the acidity of that solution. Acidity is referring to the concentration of the hydrogen or hydronium ions. pH is a logarithmic scale or a base 10 scale. This means that as the pH of a solution changes by a factor of 1, the concentration of the hydrogen or hydronium ions is changing by a factor of 10. So the two variables that we're looking at, pH and concentration, vary by a factor of 10, not by a factor of 1. To calculate the pH, we can use the formula pH is equal to the negative log of the hydronium ion concentration. The square brackets that you see around the hydronium refer to concentration in moles per liter. So in the examples that we're going to do here to follow, use your calculator and put in the negative log of these values. So for the first one, 1 times 10 to the negative 3, this is a concentration that's in moles per liter. And when you do the negative log of that, you should come out to a pH that is equal to 3. Don't forget about that negative part in the calculation. The second one, 1 times 10 to the minus 10, and again that's moles per liter, when you put it into the formula and calculate, will give you an answer of pH equal to 10. And the third one, 1 times 10 to the minus 18, when you calculate it, will give you a pH that is equal to 18. Notice that these pH values have no units. So when we change from a concentration in moles per liter to a pH, we have no units on those numbers anymore. Also, if you look at the concentration, the 1 times 10 to the something, and the pH value, the negative exponent on the 10 is giving us that pH value. So the 1 times 10 part at the beginning is related to our number, but the most important part is that negative exponent. So the negative 3, the negative 10, or negative 18. You might also be wondering about a pH of 18. The scale that you learned from 0 to 14 or 1 to 14 are just the most common pH values that you might come across in solutions that you would encounter within your life. The scale can actually go below 0, so you can have negative pH values, and they can go above 14 as well. So let's do a couple of examples where we have numbers in concentration that are not just 1 times 10 to something. So in this first example, we have a sample of pool water with a concentration of hydronium ions of 6.42 times 10 to the negative 6 moles per liter. So from that negative 6 exponent on the 10, we should know that we're coming out to a pH of somewhere around pH 6. It's not going to be exactly that because of that base number of 6.42. So if we use the formula, negative log of the concentration, so 6.42 times 10 to the negative 6, and put that into your calculator, you should come out with an answer of 5.192. So that's pretty close to the pH of 6 that we would be expecting from that exponent. In our second example, we have a sample of drain cleaner that's analyzed and found to have a hydronium ion concentration of 4.28 times 10 to the minus 13 moles per liter. So again, from that exponent, we can figure out that calculating the pH would give us somewhere around pH 13. So again, using the formula, negative log of the concentration, which is 4.28 times 10 to the minus 13, you come out to a pH of 12.369. So we're pretty close to the pH of 13 that we were expecting. pOH, this new term, is a measurement of the basicity or alkalinity of a solution. So basicity and alkalinity just mean the concentration of hydroxide ions. Again, this is a log scale, meaning it's a base 10 scale, and it is related to the pH, which we will get into in just a little bit. If you have a look at the formula for how to calculate pOH, it looks almost exactly the same as the formula we had to calculate pH. The difference is which concentration we can use in the calculation. So for pH, we were using hydronium. For pOH, we have to have the concentration of hydroxide. And again, we're not going to have any units on those pOH values. So if we want the pOH of a solution that has hydroxide ion concentration of 1 times 10 to the minus 3 moles per liter, pOH will be equal to 3. And if we have a solution that has hydroxide ion concentration of 1 times 10 to the minus 8, pOH will be equal to 8. In this example, we have a concentration of hydroxide ions of 3.47 times 10 to the minus 4 moles per liter from a solution of baking soda. And to calculate the pOH, we want to take our formula from above and just substitute in that concentration. So pOH is equal to negative log of the concentration of hydroxide, which is 3.47 times 10 to the minus 4 moles per liter. So putting that into your calculator, you come out with 3.460. Now remember, this is a pOH, and we have a basic solution. So this does actually make sense, even though you're not as familiar with the pOH scale. If we want to do a reverse calculation, so if we have pH or pOH and we want to find concentration, then we have a slightly different formula. So to calculate the concentration of hydronium ions in moles per liter, we would do 10 to the exponent negative pH. If we need to find the hydroxide ion concentration, we would do 10 exponent negative pOH. So make sure you have the proper pH or pOH for the calculations. So first example, calculate the concentration of hydronium ions in an acidic sample with a pH of 3.920. So concentration of hydronium, and you don't have to use the square brackets, but I'm going to, equal to 10 exponent negative 3.920. So when you put that into your calculator, which should be the second function of your log button, you come out to an answer of 1.20 times 10 to the negative 4. And we want to put the units of moles per liter back onto these because they are concentrations. Second example, calculate the concentration of hydroxide ions when we have a pOH of 12.453. Again, square brackets for moles per liter of hydroxide. And 10 exponent negative pOH, so negative 12.453. And in your calculator, if you enter this correctly, you come out to an answer of 3.52 times 10 to the minus 13 moles per liter. Now what we need to consider is the relationship of the pH and the pOH to each other. If we take any sample and measure its pH and its pOH, those two numbers added together would give us 14. You might remember that the scale you're familiar with went from 0 to 14, and that's sort of related to what we see here. In the first example, we want to calculate the pH of a sample that has a concentration of hydroxide ions of 3.60 times 10 to the minus 2 moles per liter. If we have hydroxide ion concentration, we can't calculate pH, but we can calculate pOH. And from there, we could calculate pH. So from the hydroxide ion concentration, we can calculate pOH. So for that, we want to say negative log of the concentration, so 3.60 times 10 to the minus 2 moles per liter. And in your calculator, taking that negative log will give you 1.44. Now to get the pH, we can do 14 minus the pOH of 1.44, and we end up with 12.56. For the second example, we want to calculate pH and pOH of a solution where we've dissolved 0.784 grams of barium hydroxide in 900 milliliters of water. This equation is going to have a few different steps to it. First thing we want to look at is the barium hydroxide and what happens when it dissolves. Barium hydroxide is one barium ion and two hydroxide ions. So when this dissolves in water, we will end up with one barium ion, that's 2+, and two hydroxide ions that each have a charge of -1. The 0.784 grams is the mass of the barium hydroxide compound that we started with. So from that mass, we're going to have to do a few calculations to get to the concentration of the hydroxide ions, and from there we can find pOH and pH. So first we want to calculate the concentration of the barium hydroxide compound. So from the 0.784 grams, we are going to need the molar mass so that we end up with moles. So the molar mass of this compound is 171.35. And we're also looking for concentration, which is moles per liter. So we want to divide by 0.9 liters. That's going to give us a concentration of 0.00508 moles per liter. And remember, that's the original compound, barium hydroxide, but it's not necessarily the concentration of the hydroxide ions. If you look back at the dissociation, you'll notice that we get two hydroxide ions for every one of the original compound we started with. So the concentration of the hydroxide ions, therefore, is going to be twice as much. So the 0.00508 moles per liter times 2 moles of hydroxide ion for every 1 mole of the original compound. So the concentration of hydroxide is 0.0102 moles per liter. From that concentration of hydroxide, we can calculate the pOH. So pOH is negative log of the concentration. So that's 0.0102. So negative log of that number gives a pOH of 1.993. And the pH we can find from doing a 14 minus the pOH. So we come out with a pH of 12.007. The last thing you need to consider is the significant digits of pH and pOH values. The rules for significant digits for these two numbers, because they are based on the log scale, is a little bit different. If you have a pH or a pOH value, the significant digits are only the digits that follow the decimal. So in the first pH value that's given here, 12.43, the 4 and the 3 are the only two significant digits in this number. When you are doing your calculations, that's going to make things look a little bit different. But if you look back at all of the examples that were done, they do have the proper number of significant digits for the pH and for the concentrations. In the second value, the pOH, 2.6529, the 6529 are the significant digits. So there's 4 significant digits in the second example number that I've given here. So if you need to, go back and look at all of the examples that we did. These will look a little bit strange, but you need to know these rules for significant digits in your calculations.